we'll finish up our study of combinations by doing a few more identities. This first one here asks us to look at a way to expand 2 to the n using 1 plus 1 to the n via the binomial theorem. So let's go ahead and do that just algebraically. So that would say that 2 to the n is equal to 1 plus 1 to the n, which is equal to the summation of n choose k times 1 to the n minus k times 1 to the k, where k goes from 0 to n. But 1 to the n minus k is just 1, and 1 to the k is just 1, so that's equal to the summation k equals 0 to n, and choose k. So the binomial coefficients are somehow related to the power of 2 to the n. And here's a way that we can describe this from a counting standpoint. So this side here, 2 to the n, is the total number of subsets of a set of n elements. Maybe you remember us doing that back earlier. So that is an earlier result. You can look back and see where we did that. 2 to the n is the total number of different subsets of a set of n elements. The right-hand side actually will count these according to how many elements are in a set. Then 2 to the n is equal to the number of subsets with 0 elements plus the number with 1 element plus the number, I'll abbreviate, with 2 elements, etc. But that's equal to, how many have exactly 0 elements? Well, there's only one of those. That's the empty set. Let me write that again. That's the empty set. Has 0 elements, plus the number that have 1 element would be the number of ways you can choose one thing out of n. So that's the number of 1 combinations, plus the number of 2 combinations would be the number of subsets of size 2, the ways you can take 2 of them, plus all the way out to n to the n, the number with n elements, and there's just one of those, of course. So this is n choose 0, actually, the first one, just to tie it into the formula above. Sure enough, that's what we get when we look at the right-hand side from a combinatorial standpoint. So this is what we did. We explained the identity using a number of subsets. I didn't actually tie it to that particular set, but a set of size n. So I'm going to give you a couple more identities here. We don't have a whole lot of space here on the slide that remains here, but I'm going to give you Pascal's identity. And in the printed shell that I posted, these are contained in that. So Pascal's identity tells us that n plus 1 choose r, n plus 1 choose r is equal to n choose r plus n choose r minus 1 for integers 1 less than or equal to r less than or equal to n, like so. So this can be done from a algebraic standpoint. You can churn through the formulas for the binomial coefficients and show this, easy enough, but it can also be done from a combinatorial method, meaning a counting way. So what I'm going to do is look at the left-hand side. The left-hand side is equal to the number of subsets of R elements from the set 1, 2 through n plus 1. Any set of size n plus 1 would work here. And it just makes it more convenient to work with 1 through n plus 1 in our writing instead of using things like A1, A2, etc. So any set of n plus 1 elements. All right, now each of these, each subset of our elements, either comes from the first n of these. There are n choose R of these from 1, 2 through n, and separately n choose R minus 1 of these with R minus 1 elements of 1, 2 through n, along with n plus 1 thrown in. So just to make sure this last one makes sense here, what I'm saying is there's two ways to get these. First of all, take all of them from the first n of them. Second, take n plus 1, and then you need R minus 1 more of them from the first n. And those are two separately different ways to form a subset of size R, and so that gives us the total number of subsets there. There's one more identity that I want to describe here, and so I'm going to do that. I'm not going to have space on this sheet to actually prove it. I didn't set this up to do that, but I did want to capture all the notes to be able to post those. But let me do one more here, and I'll use the green here to give you Vandermon's identity. And that looks like the following. Vandermon's identity says that if you have two integers and you add them, m plus n, and you take m plus n choose R, then that's a summation as k goes from 0 up to R, that's an R up there, of m choose k, so k of the first set, so to speak, n choose R minus k, like so. And there are some conditions on there. The conditions basically being that R is less than or equal to m, and R is less than or equal to n. So I think I will describe this, but not right in this video here.